This video is brought to you by Wondrium. You can sign up for free and support this channel by clicking the link in the description. Physicists study how the universe works at the most fundamental level. They're like Sherlock Holmes. They've just come to the scene of the crime, which is the universe. And they're looking high and low, trying to find clues that can tell them what happened, how things came to be, but also how it all works. If you ask a physicist, what makes the universe tick? What's at the core of physics theories? One of the common answers you'll hear is symmetry. Symmetry lies at the heart of physics, and it appears to be a fundamental property of the universe. And it leads to something quite profound. You see, every symmetry leads to a conserved quantity. For example, it leads to the law of conservation of energy, the idea that energy overall is neither created nor destroyed, it only changes form. Similarly, conservation of momentum and electric charge. And it even leads to fundamental forces, such as the electromagnetic force. So, what is symmetry? How does it play a role in physics? And how does it lead to some of the most fundamental rules the universe seems to obey? The answer will probably shake your idea about what physics really is. And that's coming up right now. What is symmetry? Symmetry is about actions. Actions that in some sense don't change anything. This might sound like a stupid concept. If you don't change anything, then what's the point of doing anything? Well, let's look at that. You might have unknowingly studied symmetry in one of your elementary school classes. For example, if you played with a mirror and geometrical objects. Consider an equilateral triangle. This is a triangle where all sides and angles are equal. In this case, we can put a mirror from one corner to the middle of the opposite side. If we do this and look into the mirror, the reflection of the image will complete the triangle. Each side is a mirror image of the other side. This is a symmetry of the equilateral triangle. But we can do more. There's another operation we can do, which recovers the original triangle. Consider rotating the triangle by 120 degrees. Again, the triangle will look identical to what it was before. Now, the problem is that we can't see the change, so to help us understand the symmetry of this triangle, let's write the letter A in it. This will help us identify the permutations. Let's start from the beginning. The initial position is one permutation. Then we can mirror it. This gives us another permutation. Then we can rotate by 120 degrees. This gives us a third permutation. Again, we can consider the reflection giving us the fourth permutation. We can rotate another 120 degrees to get the fifth permutation, and consider the reflection to get the sixth permutation. Now note that the next time we rotate 120 degrees, we end up where we started. Conclusively, there are 6 permutations we can do with this triangle. Now, you're probably asking, why are you wasting time on elementary school math? Well, let me reveal the secret of this exercise. What we just talked about is a simple example of something much more complex, namely group theory. Group theory is the math behind symmetries. The mathematics behind the symmetries of the equilateral triangle is called the dihedral group of degree 3, where 3 refers to the triangle having 3 corners. We can also say it's of order 6, as there are 6 permutations, also called group elements. As another example, if we considered the symmetries of a square, the group theory behind it would be the dihedral group of degree 4. Going back to our triangle, notice how we were able to change between the elements or permutations using 2 different operations, rotation and reflection. We can move between all elements using combinations of these operations. So we have 2 ways of describing this group, either by considering the list of all elements or by the operations we perform. In this case, reflections or rotations. In mathematics, we call the latter generators, because from the generators of the group, we can produce all the elements of the group. You might ask, well, what's the problem with having just a list of elements? Well, it's fine for a simple group, but consider how many elements there would be if we did this for a hexagon. which is a more complex dihedral group of degree 6. Just like with the triangle, the generators are reflections and rotations. The point is, it's a lot shorter and simpler to describe a group in terms of the generators than a potentially long list of elements. And to make matters worse, groups can have an infinite number of elements, making it impossible to describe them without generators. Before moving on, let's consider the importance of group theory, because this is where the magic begins. Group theory is simply the math behind the symmetries. I said in the beginning that symmetry is about actions that in some sense doesn't change anything. What I meant with actions is applying the generators to a group. And as we have seen, the result of applying a generator doesn't change anything visible. The key here is that it's not the same as nothing changed. The object has been transformed, but it looks the same. This is the key. We can do something, but in the triangle it holds its shape. It remains the same. And in general, we stay within the group elements. Overall, what I want to impart is that symmetries gives us the rules for how to transform something while conserving a quantity. In the case of the triangle, that conserved quantity is its shape, and the transformation is rotation and reflection. This leads us to what's called Noether's theorem, developed by Emmy Noether around 1915. This theorem states something profound about nature. In its simplest form, it says that for every symmetry, there's a corresponding conservation law. This is huge. This directly connects symmetries with conserved quantities. For example, time translation symmetry, which is the idea that the laws of physics are the same today as they were yesterday, as they will be tomorrow, leads us to the principle of conservation of energy. And space translation symmetry, which is the idea that the laws of physics are the same here as they are 10 meters away, or on the moon, or anywhere else in the universe, leads to the law of conservation of momentum. Similarly, the fundamental forces of nature also arise from certain symmetries. So we looked at triangles and polygons earlier, but what happens if we take the limit of having a polygon with an infinite number of edges? We get a circle. A circle of some radius r can be described on a 2D xy plane using polar coordinates by these equations. If we make the simplification that the radius is 1, we simply get the following. Two equations which are functions of the angle phi. This is what we get using real numbers, but it limits us mathematically. If we allow ourselves to use complex numbers to represent the circle, we can write it with just one equation, where r is the radius, e is Euler's number, representing a constant, and I is the square root of -1. It's called an imaginary number. Since we chose the radius to be 1, we can simplify it to just this. This allows us to write one complex equation that achieves the same mathematically as two real equations. This single complex number z can describe any point on the circle of radius 1. All we had to do was change one axis to be imaginary. So the circle is on a complex plane. This shows how complex numbers can be powerful math tools. Notice the point on the circle is completely determined by the angle phi. It turns out that there's also a symmetry group associated with this circle of complex numbers with a radius or magnitude of 1. It's called the U1 group. The elements of the group are all the infinite possible angles phi around the circle. We can write the transformation of the U1 group formally as follows, where n is the generator, meaning n represents how much we rotate around the circle. Now, where have you seen complex numbers in physics? In quantum mechanics. It's built on complex numbers. Let's try to apply the symmetry of just moving around the circle with this simple transformation. To describe fermions, which are matter particles, we need some equation of motion that describes their behavior. To do this, we can use the Dirac equation. Now, I know this is a scary-looking equation, but don't be intimidated by this. You don't have to understand the math. I just want you to see the equation so you can see conceptually what happens to the math when we do these transformations. L is the Lagrangian. A Lagrangian is just the difference between kinetic and potential energy of a particle. Psi is the wave function of a matter particle, and psi bar is the wave function of the equivalent antimatter particle. The wave function, if you recall, when squared, tells us the probability of finding the particle in a given location when measured. The first part in the parentheses describes the particle's movement in spacetime, and m is its mass. Okay, so this equation describes some matter particle, like an electron, with some mass m moving in space. You might say, okay, so what? I don't see any forces here. This is where group theory comes in. If U1 symmetry exists, it would mean that if we applied our transformation to this equation like so, where n is -1 for matter particles and 1 for antimatter particles, the Lagrangian would not change. The problem is that when we do this, the Lagrangian does change. So this tells us that there's no U1 symmetry, and we wind up with a broken theory. However, if we modify the equation by adding a new quantum field to the theory, a so-called gauge field, we can get a symmetry. Another name for a gauge field is a force. So when a force is added to the equation, we find that a symmetry exists. Our theory then works and obeys U1 symmetry transformations. So what is this force that we just added? It turns out that this new term that was added to the equation describes the electromagnetic force. The E in this case is not Euler's number, it's the electric charge, and represents the photon field. So this tells us that photons are the force particles that mediate the electromagnetic force. So while we had electrons in the initial Dirac equation with no interaction, what we have here is an equation with electron-to-electron interactions, mediated by the photon field. The full equation looks like this. The additional term in front contains what's called the electromagnetic field strength tensor, which is also defined from the photon field. This term essentially contains all of Maxwell's equations. Notice what happened here. We took a theory for fermions and demanded a U1 transformation. Adding the additional mathematical terms to make the symmetry work gave us the electromagnetic force mediated between fermions by photons. This is the theory of electromagnetic force, also known as quantum electrodynamics, or QED. We ended up with the entire theory of electromagnetism just by demanding one relatively simple symmetry. Because of Noether's theorem, we know something is conserved. In this case of the electromagnetic force, electric charge is conserved. And as it turns out, the standard model is constructed to respect these symmetries or special unitary groups, U1, SU2, and SU3. Sometimes if you ask a mathematician, they will write the entire standard model in terms of these groups. When scientists say that they're studying group theory, they're studying the mathematical symmetry transformations of objects or abstract things. It turns out that each group leads to a symmetry resulting in a conservation law and a fundamental force. As we saw, the U1 group gives us the conservation of electric charge. It's a symmetry associated with the electromagnetic force. The SU2 group gives us conservation of weak isospin or weak charge. This symmetry is associated with the weak force. And as you might guess, SU3 group leads to conservation of color charge and is associated with the strong force. It leads to the theory of quantum chromodynamics. In other words, the three symmetry groups that the standard model respects gives us three of the fundamental forces of our universe. And we can do similar mathematical exercises as we did for U1 for SU2 and SU3 groups, but the math is much more complex. The U1 group is like a one-dimensional sphere or circle, but you need 2 dimensions to visualize it because a circle transforms on a 2D plane. Similarly, the SU2 group is like a 3-dimensional sphere that transforms in 4 dimensions, which we can't visualize. And SU3 symmetry is even more difficult to visualize because it would be an 8-dimensional sphere that requires 9 dimensions to visualize it. Now, you might think this is pretty cool, but it gets even cooler. Remember that the generators are like the rules for how to transform while respecting symmetry. The U1 group has 1 generator because there's just 1 rotation around a circle. Now ask yourself, how many bosons are responsible for mediating the electromagnetic force associated with this group? Well, it's just 1 single particle, the photon. It turns out each generator of a gauge group corresponds to a force-mediating particle. So with the SU2 group, which results in the weak force, there are 3 generators. Since there are 3 ways to transform a 3D sphere, well, it's mediated by a total of 3 bosons, the W+, W-, and Z bosons. Likewise, the SU3 group has 8 generators since we're dealing with an 8D sphere. So it should come as no surprise then that the strong force is mediated by 8 different gluons of different combinations of color charges. Symmetries seem to be the foundation of the laws of physics. Why this should be the case is something no one can really answer. Most people subjectively find beauty in symmetries. Even people with more symmetrical faces are considered more attractive. Maybe the universe itself finds beauty in symmetry too. And if you want to go further into the details of symmetry and also how it is fundamentally at the core of physics, I highly recommend a lecture available on Wondrium, today's sponsor, called The Power of Symmetry. It's part of a 12-chapter course called The Higgs Boson and Beyond, taught by someone you might already be familiar with because I interviewed him on this channel last year and is one of my favorite science educators, Sean Carroll. In an effort to explain our search for the Higgs boson, Sean reviews everything from quantum field theory to particle physics to symmetry. It's a must-watch for physics enthusiasts. You'll find Sean and many other fantastic educators on Wondrium. That's why I've been a member of Wondrium for years. I couldn't recommend them more, and that's why my testimonial is even at the bottom of Wondrium's homepage. It's really easy to sign up because they're offering a free trial, and you can cancel at any time. If you want in-depth college-level knowledge about all the things I talk about on this channel, then be sure to click the special link in the description to take advantage of this free offer. That link is wondrium.com/Arvin, wondrium.com/Arvin, and you'll be supporting this channel when you sign up, so I thank you for that. And if you enjoy content like this, then be sure to hit the subscribe button so you can be informed the minute I post a new video. And I'd love to hear your comments or questions, so please leave them in the comment section. I'll see you in the next video, my friend.